students, we have been discussing about these different free energy functions and models for calculating free energy of the solid solutions. Today we are going to extend that for the understanding of phase stability in heterogeneous systems. I hope you have some idea about heterogeneous systems. You know, heterogeneous systems will always consist of more than one phase. So therefore, the stability of different phases will dictate the phase transformations. So we are going to take examples of different systems and show you how we can find out the heterogeneous phase equilibria and also find out the stability of different phases from the free energy composition diagrams at different temperatures. So I am going to use blackboard for detailed discussions. So I request you to follow it very carefully so that you do not forget, because these free energy composition diagrams will be utilized in every chapter of phase transformations. So you must have a fair idea about how to construct them and how to study these free energy composition diagrams. Let us suppose we have a system, simple heterogeneous system consisting of two metals A and B, and for the sake of simplicity let us assume A has a FCC crystal structure, B has a body centered cubic crystal structure. So A has face centered cubic crystal structure and B has a body centered cubic crystal structure, and because they have similar crystal structure, therefore they will be miscible provided their atomic size differences are not very large. And let us suppose that their atomic size differences are not very large and electronegativities are similar because they are metals, so therefore miscible and solid solutions are possible. Now if I simply consider A and B mixed together, and if I go to the board just for the sake of understanding, suppose if I have A and B and I am drawing this diagram which will be common for all your discussions. So this is A end, this is B end, and this is how B increases from 0 to 1. This is the fraction of B into the alloy. Let us suppose that A is forming solid solutions with B alpha. So alpha is a solid solution of B solute in A, correct. That means alpha is nothing but A rich solid solutions. A is more, B is less. That is why as B is less we call B as a solute, A as a solvent. So in books it will be written alpha is a solid solution of B in A. The moment you see B in A, that means B is a solute, A is a solvent. Just like in a liquid solution, suppose if I take a water in a glass, add sugar. The sugar is my solute because I add very little amount of sugar into water to get a solution. Similarly, for metals, it is the atom which is added a small quantity to an atom in a large quantity is called a solute. That is why B is called a solute, A is called a solvent. And let us also assume, so A obviously alpha is solid solution and A has a face center cubic structure, pure A. So therefore alpha will also be face center cubic structure. That is how solid solutions are defined. And let us suppose beta is a solid solution of A solute in B. That means a beta is a B rich solid solutions. A is added small quantity. Okay, so we have formed two solid solutions. One is alpha, which is face center cubic structure same as A, and which is A rich, and we have another solid solution beta, which is B rich, and it has a BCC crystal structure, right, because it is B rich. Now I will basically know the different parameters of alpha and beta, so I can calculate the free energy functions of both, and let me just draw it using different color chalks. That will help you. I will take all the color chalks from here so that it is easy for me to show you different aspects of that. So first thing I will draw is the alpha solid solutions free energy curves, and we know the free energy curves. So free energy is plotted on the x axis, that is G, okay, remember. So this is free energy versus composition diagram, and this diagram is at temperature, let us say T1. This diagram is taken as a temperature T1. Now for the alpha, let us suppose the free energy curve looks like this. Obviously free energy curve for both alpha and beta will looks like inverted parabola, and this I have shown you in the books. I am showing you for detailed analysis because it will make you clear. Okay. So that means the alpha free energy curve will start from A end and go and reach there. Let us extend it further because that will, otherwise it will create misconceptions. Correct, it is always because alpha solutions. Okay. Now so this is G alpha. Now for beta, again similar thing will happen. Okay. So once I have measured and got these free energy functionals and plotted at temperature T1 from A reach to B reach end, I get two separate curves. Now it is very clear because free energy tells you relative stability, that A reach solution alpha is stable till this point, this crossover point, you can clearly see. Okay, this is a crossover point here in which A reach solution is stable, and beyond this crossover point B reach solution or beta is stable. Am I clear? Very clearly seen that the relative positions of the free energy curves, if you compare, alpha phase has a lower free energy compared to beta phase from A reach end to this crossover. Similarly, from this crossover to the B reach end, beta has a lower free energy. Because of this, alpha is stable from these to this, beta is stable from this to this. But you know, if you clearly look at it at the crossover, actually this looks like that, but this is not a correct picture. The correct picture is little different. But if you look like that very carefully, there is a crossover. Crossover means free energies are equal at this point. So that means both the phases will be stable. When the free energies are equal at this point, that means both the phases will be stable. Correct? Let us suppose, for your understanding, even if you do not know thermodynamics, only at this point both the phases are stable because free energy is equal. Correct? But you can clearly see that even if that is the case, so this is my value of free energy. Suppose G or both will be same, so I write G, the free energy of the system consisting of certain amount of alpha, certain amount of beta, because both are stable. Correct? But if you clearly see that it can still lower its free energy further, very clearly. Why? Because it can decompose into two phases of composition, alpha of this composition and beta of this composition, and then I can draw a line. So average free energy will be given by this point now. So that means even though the crossover point tells you that free energy of both the solutions are equal, and that means the solutions of alpha and beta, alpha of this having this much of say let's suppose this much of B and beta of this much of A will be stable from this diagram. But that is not the case, because system can always decompose more alpha and more beta and then reduce its free energy. It can further do that. Okay, it can further go and reduce it to this point. That is what it can do, because the average free energy of that system will be by given at this point. So initially it was this point, then it reduced to this point, then it can reduce to this point. So further it can lower down the free energy of the system. Am I clear? This is very important concept. So now the question is that how far we can go down. That will be clear to you once I little bit erase that part and explain to you. It is very clear that if I erase these things and draw a nice plot, then it will be clear that if I draw a common tangent between these two, then I will be touching the lowest portions of these free energy curves, and therefore it cannot reduce any further below, because I cannot draw a straight line like this, then it is not fair, it is not going to be mathematically correct. So it can reduce free energy by this much delta G by actually forming a solutions of alpha having this much compositions x b alpha and this much composition of beta, correct? It can do that. So very clear, whenever you have a crossover between two free energy curves, this is a very golden rule. That means that there is a range of composition in which alpha and beta are together stable. So that's why it is here both alpha and beta are stable. But in this range alpha is stable, in this range beta is stable. Why? Because beyond this point it is this free energy curve which is lower than the alpha. Similarly below this point, below xb alpha, it is the alpha free energy curve which is lower positions than the beta. So therefore alpha is stable from a reach end or pure A end to xb alpha compositions, beta is stable from xb beta to p end. In between both alpha and beta are stable. So this is also known as tangent to curve rule. Why? Because I am drawing a tangent to the two curves. This is known as tangent to curve rule. That's why we always draw the tangent to the curves, common tangent to the curves. And this also allows us to explain that in heterogeneous system, if I extend these lines which I have been discussing with you for a long time, that this will hit B reach end here, A reach end here, okay. These are the 2 points. And I know that if I draw a tangent to the curve, that you should do yourself as a part of homework. If I draw a tangent to the free energy curve, this if this hits the A reach end, this point tells me that these are the chemical potentials of A, because it is tangent to both the curves. So therefore chemical potential of A in alpha must be equal to A in beta, right. Similarly this is also hitting here, so therefore I can write chemical potential of B in alpha must be equal to chemical potential B in beta. So that means if I draw a common tangent, I can clearly explain satisfy all the thermodynamic conditions to these phase equilibrium. So it's very clear, if I have a phase mixture whose free energies are equal at this composition at this point, let us suppose this composition is xb, okay. At this point xb0, let us suppose, it will decompose into two solid solutions. Still the compositions of the solid solutions will reach these 2 points, and these 2 points therefore can be obtained simply by drawing a common tangent to these curves. This is very important concepts, because in the next lecture I am going to use this concept extensively to arrive at stable composition range for the different phase mixtures. And I would like you to be having a very clear idea how I am drawing it and how I am explaining it. So it's very clear, if I draw that common tangent, I reduce the free energy further from this point to this point. This is my free energy of the mixture now. So the free energy of the mixture is at least lower from the free energy given by this crossover point by delta G, and this is possible only by decompositions of forming these two solid solutions. Okay, so let us keep this diagram. That tells you the basic concepts, and I told you how the free energy, the chemical potential can also be equated in this way. Now I go one by one, at least few phase diagrams, okay, and explain you how things will happen. Phase diagrams, as I told you, are very basic important things in the phase transformations, because phase diagrams tells you how the different phases will evolve and how they are going to transform. So we will take some of the phase diagrams and show you how we can use this free energy composition diagrams to explain the origin of the different phases and the transformations. First phase diagram which I will take, I will draw here so that you can understand, is the simplest possible phase diagram in metallurgy or material science. Suppose I have two components A and B. This is A rich, that means this is A pure, this point is A is 100% pure, this point B is 100%, okay, and B is increasing from this end to this end, okay. So therefore if I write in fraction, B is here 0, B is 1 here, A is here 1, B is 0, A is 0 there. So simple possible phase diagram will be like isomorphous system. and this axis, y axis is always temperature. You should know that temperature either in centigrade or in Kelvin. So let us now write it. So let me just draw the phase diagram. So phase diagram will be like a lens. Here A has a lower melting temperature than the B. These are the melting temperatures A and B. TMA, TMB. And this is a lens stable phase diagram separating liquid and a solid solution alpha. And within the lens we know both liquid plus alpha are stable. Okay, I am not going to spend any time on that because this I have discussed in my earlier course as they are in the books. Now, how do I explain thermodynamically that there will be alpha phase here, liquid phase here, alpha plus liquid here. Okay, so let us take free energy composition diagrams like this at different temperatures. Let us suppose I take at this temperature T1, I take at this temperature TMB, I take at this temperature T2, I take at this temperature TMA, and I take at this temperature T3. These are horizontal lines just like a tie line in a phase diagram. So I have taken one temperature above the melting temperature of both, that is TMB and TMA, that is a T1. I have taken a temperature which is exactly TMB. I have taken a temperature in between this liquid plus alpha, that is T2, taken a temperature at the melting temperature of TMA and a temperature T3 which is very low temperatures where only the alpha phase is stable according to the phase diagram. So let me just draw these free energy composition diagrams here on this board. So how many diagrams will be there? 5, because 5 temperatures 1, 2, 3, 4, 5. Okay, this is also TMA. So I will draw 5 diagrams, 3 at the top and 2 at the bottom. Okay, so for each case this is free energy, so G, G, G. Okay, and this is A, this is B. While you draw any diagram, you must be first labeling your axis. This is, otherwise there is no point in showing the diagram. So I will be drawing at temperature T equal to T1 first. So I have, obviously first thing I have to look at is that in this phase diagram there are only 2 phases possible. One is a liquid solution, otherwise is a solid solution alpha. And we always put solid solutions as a Greek alphabet as to the phase diagram. Why? Because these Greek alphabets are easy to use, and also this is a convention. So it starts with alpha, go beta, gamma, delta, slowly one by one form in the Greek alphabet series. So obviously at temperature T1 it tells you that liquid is the stable phase. You can see here alpha is not stable at all. So that means at all compositions from A reach to B reach, alpha free energy curve will be, liquid free energy curve will be lower. So liquid I am drawing using a blue color liquid, and because liquid is only stable, alpha is not stable, so alpha free energy curves will be the higher position relatively. Stability tells you whichever is the lower position, that phase is more stable. That is very easy to understand. There is no crossover. There will be no crossover because it is only the alpha phase is stable. So what happens then at temperature T equal to TMB at the melting temperature of B? Okay, you clearly see our liquid is stable all throughout except at B end. Here there is a both the curves actually meeting, liquidus and solidus. So that means free energy curves will also meet at the temperature because both must be stable, alpha liquid at the B end. So that's only possible when, so I draw first the liquid, okay. Now I draw the alpha is stable all through except at B reach end. Oops, yes. No, something wrong. This has to be alpha. So you can clearly see at the B end only these two curves are meeting. That means free energy of the solid alpha solid solution and the liquid L solid solutions are same value at this temperature. So because they are meeting only at that point, so there is no crossover, only meeting point. So there is no point in drawing a common tangent. Now what happens when I draw at temperature T equal to T2? That is the temperature between these two phase fields. So what will happen? Let us see what happens. So first, obviously because both the phases are stable, there must be a crossover, as I told you from there. From the first diagram, it is very clear there will be a crossover. So liquid and alpha, so liquid will be, sorry, this is alpha, not liquid, and correct. You have to raise a little bit, otherwise it will not match. Okay. So first let me draw the liquid Gl, and I will draw now the alpha. It is very clear that liquid is stable at the beginning in the A reach end some part, then liquid plus alpha is stable and then alpha is stable. So that is why this crossover point here. So now once I have a crossover point, I need to draw a common tangent because I told you the reason for that just now. So I draw a common tangent, and this common tangent will divide the whole region into three parts. So obviously this is liquid, because you see the liquid free energy curve is lower positions. This is again making mistakes, this will be alpha again. So therefore this is at liquid, and then again beyond these compositions alpha is stable, so alpha, and between these two the phase mixture of alpha and liquid is stable. That is what is seen in the phase diagram. So that means it very clearly says you that in the temperature regime between Tm beta and Tma, these two phase mixture will be stable. We will draw first the Tma, then it will be much clearer. So at T equal to Tma, if I draw the free energy curves, you can clearly see alpha is stable all throughout except that at the A end both liquid and the alpha the liquidus and solidus curves are meeting. So let me just draw it. So therefore alpha is stable, alpha will be always lower position, and liquid will be always higher positions. Only at this point they are meeting, because at this point A point these two are meeting, so that means both solid and liquid are stable. That means at the melting point of A both the solid and liquid will be stable, that is obvious. At 0 degree Celsius both ice and water are stable. Okay, so that means very clear from Tmb to Tma only these crossovers will take place. That below Tma, Tmb and above Tma only these crossovers will take place, and the reason why that because of that the alpha and liquid both will be stable. And this one last temperature, which is T equal to T3, obviously all throughout alpha is stable. So I draw it alpha and liquid. This is opposite to these T1, these positions of the curves. So that means by using my free energy composition diagrams, I can explain the phase stabilities in these phase diagrams. So few things you must remember. One, that free energy curves are always inverted parabola, that I have explained you why. Second, that relative positions of the free energy curves will tell you the stability, which phase is stable. More, it will have free energy positions lower than the phase which is not stable. Third, whenever you have a crossover of the free energy curves, that indicates that there is a composition range in which both the phases will be stable, or all the phases will be stable rather. It can be that 3 free energy curves will be crossing over, so then three phases will be stable also. But here, because it is very simple phase diagram, easy to understand, only 2 free energy curves are crossing over. So crossing over means there is a composition range in which both alpha and liquid is stable. And fourth thing, you must remember that these free energy curves must be drawn from one end to the other end. Never ever leave in between, because that does not look good. Obviously, the phase may not be stable from pure A end to pure B end, but free energy curves can be drawn, because we can always obtain the free energy informations or free energy curves, free energy functions can be obtained and plotted. So, in a nutshell, I just wanted to show you that how these free energy composition diagrams can be used for simple phase diagrams. Now, in the next lecture, I am going to take you some more examples so that you feel more confident and you can yourself draw it. So, the moment you draw yourself in a notebook while listening to this lecture, you will have more confidence of doing that. Because phase stability, phase diagram, phase stability and the transformation of the phases, they all actually related to thermodynamics and kinetics. And thermodynamics is best explained in material science by drawing diagrams. And this is one such critical diagrams which you must learn very well. Okay, next we will do the eutectic phase diagrams that I will show you in the next class.